What we want to do here is we want to look at the table of values here, the x values and the y values. Does this table below represent a linear function? Why or why not? There are a couple of ways that you can do this. Now the first way that you can do this is by graphing the ordered pairs. And so let's go ahead and do that. Let's graph the ordered pairs out. I've got the ordered pair here 1, 3, so I go out 1, up 3. 1, 2, 3. There's an ordered pair. And let me change the color because I've got them set to white right now, so let's try that again. So out 1, up 3, there we go. 3, 7, so out 3, up 7. -1, -1, so left 1, down 1. -2, -3, left 2, down 1, 2, 3. And 0, 1, 0, 1. And so graphically, it appears that everything is setting itself up to look like a straight line. Well, that's one way that we could do it. However, you got to also know this. It may look like a straight line, but that doesn't guarantee us anything. So even though you may graph it and get the answer correct by saying that it is, there are some graphs that could look like straight lines but don't necessarily have to be. For example, if I take this point right here and just shift it just a little bit. Now everything's graphed perfectly here in my program and you can see that it doesn't follow suit. But if you were doing this by hand, how could you tell that this point right here doesn't really exist on the line? You couldn't. So there's got to be a better way. And the answer is, there is a better way. And the better way to do that is by finding the rates of change. So if I take this table right here, as a matter of fact, I'm going to go ahead and take a snapshot of this table right here. What I'm going to do next is I'm going to go ahead and I'm going to find the rates of change between all of the points. Okay, let's go ahead and look at the rates of change of the points. So I've got my snapshot here. I'm going to close that window. And the way that we do the rates of change is we use our slope formula, m, which is y2 minus y1 over x2 minus x1. So the y values are in the second row and the x values are in the first row. We're going to call the number 7 y2. We're going to call the number 3 y1. So 7 minus 3 over 3 minus 1 is equal to 4 over 2, which gives us 2 over 1. So we get a rate of change of 2 units for every 1 unit, or 2 over 1. That's our first one. Now we use this -1 here as the y2, and this as the y1, this as the x2, and this is the x1. So -1 minus 7 over -1 minus 3, which is -8 over -4. Now, a negative number divided by a negative number is a positive. So I'll make both of these positive signs. 8 divided by 4 is 2, so I get 2 over 1. So far the rate of change stays the same. Now I use this as my y2, and this is my y1. This as my y2, and this is my y1. So -3 minus -1 over -2 minus -1. Now, when you have two negatives come together like this with parentheses, and there's no power, we have a good old classic case of the bump rule. So plus, 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 plus. So -3 plus 1 is -2. -2 plus 1 is -1. And once again, a negative divided by a negative is a positive. So I get positive 2 over 1. So far the rates of change are all the same. The last one, we use this as the y2 and this is the y1. This as the x2 and this as the x1. So 1 minus parenthesis -3 over 0 minus parenthesis -2. Again, we've got the bump rule. No power up here, so we can go ahead and say plus, 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 plus. And so we get 4 over 2, which reduces to 2 over 1. So the rates of change between any 2 points is still 2 over 1. And that's what guarantees me Yes, this is a linear function.